Okay, so this is a tiny bit of a work in progress. I'm still kind of finalizing the midterm exam, but I'll talk about it a bit now. I might make a few small changes here, um, but this is kind of what I've got in mind. Okay, so we'll have our midterm exam next Wednesday, and we'll have 2 live sessions. One will be at 9 a.m. and one will be at 6 p.m. Okay. The exam will be an hour and a half. And that includes also time to kind of upload. So it's not going to be, we've got 2 midterm exams. So neither of them are going to be really, really long. So probably like hour and 15 for the exam and then 15 minutes to upload, or maybe hour and 20 for the exam and 10 minutes to upload, something like that. Okay. That's kind of the estimated time. And I think it'll be the right amount of time here. Okay. Exams are open note and open book. And so that does kind of considerably, I think, reduce some of the challenge and stress of it, but I can't think of a better way or another way that would be kind of fair for everybody. But anyway, so no collaboration allowed. And then, it'll be proctored via Zoom. So you'll just log into Zoom just like you are now, except you'll have everybody will have their cameras on. And that's just kind of to make sure that you are taking the exam alone and that you're not like having some kind of party where you're taking the exams together or something. But yeah, that will be it. Okay. And it's going to be mostly pen and paper, or pretty much entirely pen and paper. If you have an iPad, you can write your responses directly on the PDF, but I'll post a PDF onto CCLE, and then you'll download that. You can print it out and you can write your answers directly on the printed pages. If you don't have a printer, that's fine. Just get some blank pieces of paper and then just number your problems very clearly, and you'll write your answers on your blank pieces of paper. And then to submit, you will take pictures of it or scan it. I'm assuming you all have some kind of scanner app. If you've never scanned a document with your phone, please practice that before next Wednesday. You don't want the day of the exam to be the very first time you've ever done this. So please at least try scanning something there, and then you will then take the thing and you'll upload it to Gradescope. Okay. All right, so these are the kind of the problems that I've got in mind. I've got 5 problems lined up here. All right, so one will be, you'll have to find some derivatives, vector derivatives here, and I'll give you some kind of arbitrary function in vector notation, and you will find the gradient of the function with respect to some kind of vector, right? And so in the notes, you can look at the OLS loss function in vector form, and you can see how we took the gradient or the derivative of the function with respect to w, and this will be done in kind of vector notation. And on the exam itself, it won't be the OLS loss function. It'll be something a little bit different, maybe a tiny bit more complex, but nothing that's too crazy. Okay. You'll do some manual gradient descent, okay? And so I'm going to provide some kind of function, some 2-dimensional function. I'll provide some arbitrary starting point and some arbitrary value for the learning rate gamma. And then you'll manually calculate, the location, after, in 2 iterations. So you'll see, if you start here, you'll have to calculate the gradient, and then you'll do gradient descent, and you'll find the location at the next iteration, and then you'll do it again, and you'll find the next iteration as well. Okay, and so this will require you to find the gradient, and whether you Probably you'll just do partial derivatives for the gradient there, just kind of like that. So you can look up the lecture where I do gradient descent, but you'll do it manually. If you want to use R to kind of double check your work and calculate and stuff like that, that's fine. I can't stop you from doing that. But to get credit, you'll have to show your work on paper. Okay. I've got a problem for regularized loss. This might be a tiny bit too easy. I don't know, but no one's going to complain. Well, so basically, I'll give you a small data set, and that'll be like 3 or 4 points in 2 dimensions. And then I'll provide the equation that can be used for a potential line of fit. And so this might be, there might be multiple terms here, maybe a couple squared terms or something like that. All right. And then so you'll find the OLS loss. So that's pretty straightforward, right? You'll have to find the predicted value. And I will specify whether it's mean squared error or sum of squared error. So I will write, I will say, use mean squared error for OLS loss, or use total sum squared error for OLS loss. Okay. And so basically for that, you'll find the actual value versus the predicted value. You'll square it and sum them up. And then you'll find the lasso loss, and you'll also find the ridge loss, which is just a matter of kind of adding in the complexity term. So that should be very straightforward and easy, but whatever. I'm just trying to think of some problems that cover our material. Okay. This one, number 4, might be a little bit more involved. Maybe a tiny bit more tedious. Okay. I'll give you a small data set. Again, 3 or 4 points in 2 dimensions. And I'm going to provide 2 competing models. Okay. And what you're going to do is you're going to perform leave one out cross-validation for each of these models. Right. And so, for these models, I'll provide basically what the fitted line looks like when you fit it to the n-1 points. So you won't have to calculate that out. So if you have we have 4 data points, I'll tell you okay, when you fit it to these 3, this is what the predicted line is. Okay. And when you fit it to these 3, this is what the predicted line is. And when you fit it to these 3, this is what the predicted line is, and stuff like that. Okay. And so you're going to have basically n different fitted lines. And then, and you'll have to figure out kind of the cross-validation error there. So you'll figure out, how off is it for the validation point. Okay. And so you'll calculate the mean cross-validation error for the first model. You'll find the mean cross-validation error for the second model. And that will be that. Okay. Does that kind of make sense? Are there any questions as far as what that involves? Okay. And then the last part, I'll have a few conceptual questions from lecture. Some of the answers, will be taken straight from the notes. You just kind of have to find the correct passage. And then others, might require a tiny bit of thinking in terms of what would happen in this scenario or something like that. And that will be that. And yeah, so I'll finalize this just in case I make any kind of changes here, and then I'll post this online for your reference. So I'll make sure that this document's available. Okay, and so that's next Wednesday. And again, come at either 9 or 6. You don't have to tell me when you're going to show up. Just show up, and that's fine. Okay, and I hope at least one of these times will work for everybody wherever you are in the world. Okay, and if for whatever reason these times do not work for you, let me know now, and then we can try to arrange some kind of alternative arrangement. But I imagine that should cover like 98% of you or so. Okay, any other questions? We're good? Okay, then let's go ahead and get into today's lecture. All right, quick review quiz. Maybe we'll skip this, but well, okay. Well, yeah. Let's talk about it. What's the dimension of X? The input matrix X. I'll just answer these myself. Okay, X is n by 2, right? You've got two variables, n observations. So X is n by 2. W is going to be 2 by 3. You've got 2 in the input layer, 3 in the hidden layer. W2 is going to be 3 by 1, 3 in the hidden layer, 1 in the output. And then Y will be n by 1, okay? So there you go. And X is n by 2. W1 is 2 by 3. W2 is 3 by 1, and Y is n by 1. Okay, let me go ahead and give you your first view quiz answer. Today is Friday. Oh, happy Friday, everybody. We got through another week. It's already the 3rd week. Okay, end of the 3rd week. It's so fast. Okay, first view quiz answer is B. B as in bear. B. B is your first view quiz answer, B. Okay, so these are the weight matrices, and when we want to train the neural network, when we say we're going to do model training, we're going to train our model, we're going to train the network, what we're trying to do is we're trying to figure out what are the values that should go inside this matrix. What are the values that should go inside this matrix? Okay, we have the sigmoid activation function. And right now we are using the logistic function as our activation function, but you don't have to use that. A question was, do we have to use the same activation function at all layers? And the answer is no, you could use different activation functions. But for our model, we're doing a very, very simple neural network, and we're using the same activation function in both locations. But you're not required to. You can have different different activation functions, and it doesn't have to be the logistic function, it could be other things. Okay. And so this is what our loss function is. We're going to start off with the model that doesn't use biased terms. Okay. And in the following homework, you'll have to do some stuff with the biased terms. But this one, we have no biased terms. And so our predicted values are this. We do X times W1, we take the activation function there, we multiply the results by W2, and we apply the activation function there. So that was forward propagation. And basically now we want to figure out the difference between the actual values and the predicted values, and the predicted values Y hat are found using this. Now to kind of just make our lives a tiny bit easier, we're going to modify the loss function. So instead of 1 over n times the sum of squared errors, so the mean squared error here, I'm going to just multiply L by a constant, n over 2, and we're going to get J. So this is fancy J. And this is just the loss function multiplied by a constant, n over 2, and we get J is 1 over 2. And the reason for this is just to kind of make our lives easier. When we take the derivative and this square here comes down, it's going to cancel out with the 1/2, and then we can just kind of deal with the results there. But basically, because I'm just multiplying L by a constant to get J, the value that the values of W that minimize J, so we're going to minimize J, will be the same values of W that minimize the original loss function L. So that's why we're going to go ahead and do this, right? Of course, the value of J and the value of L itself will be different. They'll be off by this constant, but the values of W that do it will work. Okay. All right. So today we're going to spend the entire lecture going over backpropagation. And here we're going to take a vector derivative, vector calculus approach for backpropagation. Now, I do have to say, this is only something that we're going to do for a simple network. Okay. You know, I mentioned kind of deep learning where you have like these you know, 100 hidden layers, hundreds of hidden layers, and you have this very, very, very complicated neural network. And in that case, nobody tries to do backpropagation in the fashion that we're going to do today. Okay. At that point, you kind of just look at one layer and the previous layer, and you say, well, if this thing changes, you know, how does that change get propagated to, you know, from the previous layer and things like that. Today, we're taking kind of this vector calculus approach, and it's kind of long and drawn out, and we would really only want to do it for this, you know, a simple neural network like this. Okay, so just the big picture idea is we want to find what values should go in weight matrix 1 and what values should go in weight matrix 2. And the way we're going to do this is we want to find the weights that are going to minimize the loss function, right? So we want to find the weights that are going to minimize the loss function. The loss function is defined by this. So we want to find, I'm sorry, by this, or, you know, the loss function multiplied by a constant. And what we're doing is we're adjusting the W1 and the W2 values so that Y hats change. And so the difference between Y and Y hat is as small as possible. Okay. And to kind of minimize the loss function, we are going to achieve this using gradient descent. Okay. So, you know, wherever we are, we're going to find the gradient which points uphill, and we move in the opposite direction. We move downhill, and we keep repeating this until we get to the bottom, and that should give us something that performs well. Okay. Gradient descent doesn't guarantee that it's going to work. Sometimes it also gets stuck if you have like this flat region. So you can attempt different starting locations. But what gradient descent requires is that we have to find the gradient. We have to find kind of this multi-dimensional derivative. And so that's what we're going to do. Okay. So here's our neural network, and we want to say, all right, well, how does the loss function change if I change W by some amount, right? And so here are going to be the two gradients that we have to calculate. Okay, we have one gradient, which, you know, our first weight matrix is this 2 by 3 matrix. And so the corresponding gradient is going to be a 2 by 3 matrix of partial derivatives of J with respect to kind of the first element in the gradient, in this matrix, second element in the matrix, and so on and so forth. This over here is also kind of a matrix of partial derivatives. You know, how does the loss function change with respect to each element in the weight matrix? Okay. If we also had bias terms, we would have to calculate the gradient with respect to the first bias matrix and the gradient with respect to the second bias matrix, which, like I said, will come in a future homework exercise. But for today, we'll just look at the gradients with respect to W1 and W2. All right, so let's just do some work here. So we start off, and we've got, okay, what is the gradient, or what is the derivative of J with respect to W2? Okay, so this is going to be J is this function. Okay, so remember we took 1 over n and we multiplied it by n over 2 to get this different constant. And so if I take you know, the derivative of the sum of squares is going to be the sum of derivatives. Okay, so the derivative of a sum is the sum of derivatives. And this thing, if I take the derivative, well, the 2 comes down and cancels with the 1/2. So I get y minus y hat. And then I apply chain rule, and we say, all right, what elements in here change with respect to W2? Well, with chain rule, we have a negative sign, so we're going to multiply by -1. And then y are fixed values. The actual values are fixed, so they do not change with respect to W2, but y hat does. So we need to find the derivative of y hat with respect to y2. How does y hat change with respect to y2? Okay, well, we ask, well, what was y hat? All right, so if we think back to here, what was y hat? Okay, y hat is the result of f applied to z3. Okay, and so we can take that and we can say, well, y hat changes with respect to z3, and how does z3 change with respect to W2? So here I'm just kind of applying chain rule to split the derivative up. Okay, and so we can say, well, how does y hat change with respect to z3? All right, so again, if we looked at each element in y hat, okay, so for the nth observation, y hat is the result of f applied to z sub n in the kind of the third layer here. And so, the derivative of y with respect to zn is just f prime, right? F is our logistic function. And so this is just going to be f prime of this. All right, so then we just need to figure out the derivative of this. So the derivative of the logistic function, using kind of quotient rule, we're going to let u be 1 and v equal 1 plus e to the negative t. The derivative of this is going to be e to the negative t divided by 1 plus e to the negative t squared. All right, so here you can go over your notes and review this, but this is the derivative f prime applied to t, or in this case, f prime of zn3 is going to be this quantity here. Now, just for simplicity, I'm going to just continue leaving it as f prime, but yes, f prime itself is going to be this quantity here. All right, so to kind of to keep going, the derivative of j, our loss function, with respect to our second weight matrix is going to be this. The derivative of y hat with respect to zn3 is going to be just f prime of zn3. And we have this. Can we write f prime as f of 1 minus f? F times 1 minus f, is that true? I'm trying to think off the top of my head. Oh, is that a function of the sigmoid function? Probably. I'm trying to think of it off the top of my head. I'm pulling blanks here, but probably you might be able to pull something off like that. Okay. I believe it. Okay. But anyway, I've just got f prime here. Okay, I've got f prime here. We're not going to worry too much about this. We have a closed form solution for this, so we're just going to kind of plug that closed form solution, and we'll keep going. And so we want to say, okay, well, how does z change with respect to w? Okay, so if you if you go back to the forward propagation part, z is the result of taking the activation values in the second layer. So that's we have their hidden layer, and we multiply it by our second weight matrix to get z. Okay, so this is what we get. Okay, so z is an n by 1 matrix, and it's the result of taking the n by 3 matrix, which are the values and the output values of the hidden layer, and we're multiplying it by our second weight matrix, which are the three weight values, which is a 3 by 1. Okay, and so this is what we have. Let's look at just one value in this result. Okay, so instead of just the entire n by 1 column of z values, let's just look at one of those values. All right, so if we look at this one value, z sub n, okay, this is the result of a sub n, which is a 1 by 3 matrix, multiplied by our second weight matrix, which is 3 by 1. Okay, and so now we can do vector derivative rules. And so what is the derivative of z n3 with respect to w2? Well, that will just be an2 transpose, right? So we say, well, what's the derivative of this with respect to w2? This should be just becomes an2 transpose, and that way our dimensions line up. Okay, so we have zn3. This, when we take the derivative of this with respect to w2, this has to have the same dimensions as w2. Okay, so this is going to be 3 by 1, and we're going to have an2 transpose, which will also be 3 by 1. All right, is that okay? What's happening here? All right, so this is how it works for just one element. And what we want is we want to do it for all n elements in Z, okay? So, so our derivative so far, if we just do it for one thing, okay, this stuff so far is a 1-by-1 scalar. This y sub n is one value, y hat sub n is one value, zn is one value, and f prime of that is just going to be one value there. And here we're multiplying it by an to transpose, which is a 3-by-1. And so, you know, this, we're basically, for each value, we have a 3-by-1, and we're summing up a bunch of 3-by-1s on top of each other. So we're going to get kind of the summation of a whole bunch of 3-by-1s, which will still be a 3-by-1 matrix. Okay. Now, what would be nice is if we can just get rid of the summation. Like, can we go from individual values and change into use the vectors or the matrices and use matrix multiplication to kind of handle the summation, right? So we've got, so basically this thing is going to be a 3-by-1 matrix, and we want to, and it's the result of taking the 3-by-1 matrix for observation 1, and then we're adding the 3-by-1 matrix for observation 2, and we're adding the 3-by-1 matrix for observation 3. And basically for all n observations, we're just kind of stacking or adding up all of these 3-by-1 matrices, okay? So we can say, well, what happens if I just remove the n and I just use the vector form of this, right? So if I get rid of the subscript n and I say, well, now I've got matrix y, which is n-by-1, and matrix or vector y hat, which is also n-by-1, and I've got vector z, okay, which is n-by-1, and f prime applied to that is still going to be n-by-1, and instead of doing a sub n transpose, which is 3-by-1, if I have just the A matrix transpose, then I've got a 3-by-n matrix, okay? Now, when we do this, none of the elements, I mean, the dimensions don't quite line up, right? And so if we think about the individual values that kind of make up this 3-by-1 matrix, and we think of, okay, well, how does this work out? How do we get these things to line up? We can actually do the, we can achieve it by saying, you know what, the 3-by-1 thing that we have here is, you know, we've got n of them and we're adding them up. And so it actually makes sense to kind of bring this term to the front over here, okay? And so if you look at the individual values, I'm not breaking anything by moving this around to up here, okay? Like this thing and this thing are equivalent, right? And now if I get rid of the n subscript here, okay? So if you look at the individual values that are getting summed together, I'm not breaking anything by moving this around. I can then remove the subscripts, and now we have a 3-by-n here, okay? And this is n-by-1, and this is n-by-1, okay? And if you think of these scalar values being multiplied together, you can keep that n-by-1 multiplication, and you can accomplish this by doing element-wise multiplication, okay? So y minus y hat is an n-by-1 kind of column vector. And then Z3 is also an n-by-1 column vector. F prime of Z3 is also an n-by-1 column vector. And we want to preserve this n-by-1 shape. And so rather than trying to like transpose or multiply it, we're going to just do element-wise multiplication. This is not regular linear algebra stuff. Like if you take a vector in R and you take a vector in R and you just do regular star, it will do element-wise multiplication and you'll get the same resulting thing. And so that's basically what we're doing. We've got this vector y minus y hat, or negative y minus y hat. We've got another vector f prime of z3, and we're going to do element-wise multiplication, and that kind of preserves it. So this is going to end up being n-by-1, and we're going to multiply that by A2 transpose, which is 3-by-n, okay? And this result will be a 3-by-1, which is exactly what we want. And this is going to be the result of summing up all of these things across all n values. And so we can kind of move this around. We can rearrange these terms in here. And then when we go from the nth observation to the full matrix of all n observations, then the dimensions align. Okay, and so this result will be 3 by 1. And if you watch the Welsh Labs video, they call this delta 3. Okay, this result of being the element-wise product of these two things, which is n by 1. All right, is that okay? It was a lot of stuff and a little bit of kind of manipulation of terms here, but the result is we get a 3 by 1 matrix, which is what we want. We want the gradient of the loss function with respect to our 3 by 1 vector to be a 3 by 1 gradient. All right, let me go ahead and give you your second view quiz answer. Second view quiz answer is C, C as in cat. C as in cat is our second view quiz answer. Okay, so so that is the gradient with respect to the second weight matrix, and we're gonna do the gradient with respect to the first weight matrix. Oh, sorry, this is to kind of just wrap up. If we call this part delta 3, then the derivative j with respect to W2, or gradient with j with respect to W2, can be A2 transpose times delta 3, and that's what we have. Okay, so now we're going to do it with respect to the first weight matrix. Okay, so we're going to find the gradient of the loss function j with respect to W1, and we're going to go through our process here, same process. And so if you start, it starts off with kind of the same thing, and we say, all right, we want, so you can follow the same steps. I'm not going to repeat myself here. So far we have, how we have Zn3, the nth observation in Z. How does that change with respect to W1? Okay, and so we're going to go from there. All right, so how does the nth observation in Z change with respect to W1? Well, we're going to find, well, how does the nth observation, so W1 will affect how the nth observation in the A matrix changes, okay? Or the nth row, I should say, the nth row in the A matrix changes, all right? So we're going to find how the nth observation in Z changes with respect to the nth row in A, and then we're going to see how the nth row in A changes with respect to the first weight matrix, okay? And so we want to find the derivative, or the gradient of the nth observation, which is a scalar. How does that change with respect to the row, nth row in A, okay? So A is going to be, A is a 1 by 3 row. The nth row in A is a 1 by 3 row matrix, and you get Zn by taking the product of An2 by W2. W2 is a 3 by 1 column matrix, and so therefore the gradient of Zn3, which is a scalar, with respect to An2, which is a 1 by 3 row matrix, is going to be the transpose of W2. Okay, and so the transpose of W2 will be 1 by 3. This has the appropriate dimensions, and this is what we have. Okay, all right. So again, when it becomes your turn to find kind of derivatives for vectors and stuff, I strongly encourage that you write the dimensions underneath, because you always want to be thinking like, what are the dimensions that the result is supposed to have, and do the dimensions line up, and will I get that dimension? Okay, and if it doesn't line up, then you've probably made a mistake. Okay, and so writing the dimensions down will help you identify when you've made a mistake, because a lot of times things will not be correct. Okay. All right, so So here we're going to replace this, the derivative of zn3 with respect to an2, and that's going to become W2 transpose. All right, and so now we want, okay, well, how does the nth row in A change with respect to the W1 matrix? All right, so how does that work? Well, we're going to say, well, AN2 changes with respect to the nth row in Z. Okay, and then we want to find how the nth row in Z changes with respect to W1, right? And so again, the nth row in Z is 1 by 3. The nth row in A is 1 by 3. And so the and A is found by taking applying F to the nth row in Z. And so this is going to become F prime of this, right? And so, F happens to be the sigmoid function. We have a closed form solution for F prime. So, no problem there. We'll just replace this with F prime of the nth row in Z, which is 1 by 3. Okay. So we've got the nth row in Z is F prime. Okay. And so already we're starting to see, okay, well, we might run into some issues here. We've got a 1 by 3 multiplied by 1 by 3. We're likely going to have to do some element-wise multiplication here to kind of make sure our things align. Okay. Okay. And then this last bit is we want to see, well, how does the nth row in Z change with respect to W1? All right. So the W1 matrix is a 2 by 3 matrix. And we got the nth row in Z, okay, this 1 by 3 kind of row vector by taking the product of our input matrix X, all right, and we're looking at the nth row in X, right? So this is just observation N, which is just one row in X, which is a 1 by 2 vector. And we're multiplying that, or that 1 by 2 vector matrix by the 2 by 3 weight matrix, and we're getting, this 1 by 3 result here, okay? So we say, well, how do you find the derivative of a 1 by 3 vector with respect to a 2 by 3 matrix? Like, how is this going to work? Okay, so that feels strange. But if you pay attention to how the multiplication works between X and W, maybe we can find kind of this partial derivative, right? So if we look at the nth observation in X, right? So the nth observation in X is basically this 1 by 2. We've got xn1 and xn2, and we multiply it by this 2 by 3 matrix, okay, which is W1, W11, W12, W13, and so on and so forth. And I've colored them, the blue and the red row, okay? The result is going to be a 1 by 3, all right? And so we can kind of rely on the idea of, like if we were to do a numeric gradient check, right? And we say, well, how much would our numeric gradient change if we, because what we want to do is we want to say, how does, this change? So if I added, a small thing to any one of the elements in W, okay, then it will change the result, okay? If I add something here, then this will change by kind of xn1 times, whatever we put in here, okay? Or if I change anything in any of the blue elements, it's going to change by a factor of xn1, okay? If I change any of the values in the red row, any of the values in the second row in the weight matrix, it would change by a value of xn2, right? So if we change anything by some epsilon here in the first row, it would change by xn1. And if we change anything in the second row, it would change by xn2, okay? And so the kind of the partial derivative of zn2 with respect to W1 is going to just end up being a 2 by 1 matrix, which will be the transpose of xn. So we're going to have xn1 and xn2 in the kind of the transpose. Is that okay? So if you take this and you transpose it, then you'll end up getting kind of a 2 by 1 matrix, right? And our dimensions will align there. All right. So for the nth observation, this is what we're going to have. Okay. We've got this 1 by 1. We got a 1 by 3, a 1 by 3, and xn2 transpose will be 2 by 1. But even in this case, again, the dimensions don't quite line up, right? And so if you think about the individual values that are being multiplied together here, we can actually move this up to the front. And this feels very strange, I'll admit, okay? But if we do this, we'll actually end up getting the result that we want. So this being moved up here for the nth observation, we'll bring the 2 by 1 up here, xn transpose 2 by 1. This is a 1 by 1 scalar, and then we do element-wise multiplication between W2 transpose and the nth row in Z, which is 1 by 3, okay? And the result here, so if this will multiply out to be a 1 by 3, I've got a 2 by 1 times a scalar times a 1 by 3. That result will end up being a 2 by 3 matrix, which is what we want. So for one observation, the nth observation, the gradient of J with respect to W1 will be 2 by 3. And so now we just kind of apply the summation. So we have all of these 2 by 3 gradients, and we're applying this for all n observations to get kind of the total gradient of J with respect to W1. And so if I if I drop the summation and we go from the n to kind of the full X matrix, okay, this will become 2 by n. All of these scalar values will become n by 1 vectors, okay, and we'll continue with the element-wise multiplication here. This remains a 1 by 3, and this becomes n by 3. And by kind of applying element-wise multiplication in the appropriate places, we can preserve and keep the results to be a 2 by 3 matrix, okay? So earlier we called the product of y minus y hat and f prime of z3, we called that delta 3, but that result is n by 1, okay? And so I've got n by 1 times a 1 by 3. This is going to be n by 3. And element-wise with this multiplication, which is n by 3, so I have a 2 by n times an n by 3, and that's going to end up being 2 by 3. And that's going to be the result of the loss function with respect to W1. Okay, so all of this kind of combines, and this is what we have. So I hope, it's kind of a lot to kind of go through in one setting here, and so I hope you can kind of go through the notes, and I hope it makes sense, and I hope all of my effort spent typesetting this in LaTeX is will help you understand all of this. There were so many undersets and under brace things I had to put in here for the dimensions. Okay, so now we're going to code this up. Okay, and once you have, so the math part is the hard part, and once you get through the math part, putting it into code is, I mean, I don't know if easy is the right word, but it's pretty straightforward. Okay, so here's the sigmoid function, 1 over 1 plus e to the negative t. So I'm creating a sigmoid function of z, 1 over 1 plus e to the negative z, and that's fine. Okay, our input matrix x and y. X is a 3 by 2, and so I've got 3, 3, 5, 5, 1, 10, 2, and then our actual values of y are 75, 82, 93. This is from kind of our example. This is just the input data from our example and also from the Welch Labs video. Okay, and just to kind of get this to work, one thing that we want is, for the sigmoid function, the sigmoid function really only has value between like -5 and +5. And, if you put in something like 100, it's pretty much 1. And there's practically the derivative up there it's very flat. And so to kind of just make things work, we're going to just kind of push everything into kind of this friendly zone. So we're just dividing by 100, okay? Or we're dividing by the maximum of the column. That kind of just scales it from 0 to 1. And, we technically have values, but between 0 and 1, there's actually a derivative that exists that can be useful for us, okay? And it doesn't have to stay in that range. We're just kind of pushing things, so it kind of helps, okay? And just to kind of maintain some flexibility, I'm going to create some variables for input layer size, output layer size, and hidden layer size. And we got 2, 1, and 3. Rather than coding these in. Okay, so as far as forward feed, I'm going to create a few matrices, right? W1 is our first weight matrix. Number of rows is input layer, number of columns is hidden layer. W2 is our second weight matrix, number of rows is the hidden layer, number of columns is the output layer, okay? And then, and so forward feed, we do X times W1 to get Z, Z2. Then we apply the sigmoid function F to Z2 to get A2, and that's what I have here. Then we do A2 times W2 to get Z3, and that's what I have right here. And then I applied sigmoid to Z3 to get Y hat, right? Sigmoid to Z3 gets Y hat, right? So this is just a straightforward application of what we said is the math for the forward feed. Is that okay? All right, and then, so calculating the cost function are, I've got sum of Y minus Y hat squared, and that's going to be our cost function. So this is our current cost values for just some arbitrary starting values. I think I just plugged 1 in for everything for W1. So this is what we have. And then the derivative, F prime, e to the negative Z times 1 over 1 plus e to the negative Z squared. I guess we could also do F times 1 minus F to get our derivative, and we would get the same result. But whatever we have. Okay, and then now we're going to just code up the gradients. Okay, so we went through all of the work to figure out how this gradient, what this gradient is. Okay, so we've got Y minus Y hat, element Y's multiplication times F prime of Z3. Okay, so I've got Y minus Y hat, element Y's multiplication, just the regular star, times F prime, sigmoid prime of Z3. Okay, and a negative sign there. And then we're going to multiply A2 transpose by delta 3. So I've got A2 transpose times delta 3, the result there. And that's going to be our gradient, dj dw2. And then the other gradient, dj dw1, is going to be x transpose times delta 2. Delta 2 is the result of delta 3, which was this mess, okay? So you can kind of go back through the notes and just verify all of this. Delta 3 times W2 transpose, so multiplied by W2 transpose, and that's element-wise multiplied by sigmoid prime of Z2. And then we're going to take this result, delta 2, and multiply it by X transpose, okay? And we'll get dj dw1. Okay, so those are the gradients. And now we'll do gradient descent. Okay, so I'm going to just kind of start with some random weights. So for W1, I will start with 6 random uniform values. And for W2, I will start with 3 random uniform values. And I'm just going to kind of keep a vector to kind of keep track of the cost. And this is just my arbitrary learning rate scalar value of 5 here. All right, and this is gradient descent, okay? This is the entire algorithm. It looks like a bunch of code, but it's actually not too bad. And I realize it's 6:50. Let me go ahead and give you your last view quiz answer for today, which is D as in dog. D as in dog. Okay, I'm just going to go over a couple minutes here, okay? So this first part does forward feed. We take, our vector X, or our input matrix X, and we go through the forward feed to calculate Y hat. Okay, so Y hat is our current estimated values of Y. We're going to calculate the cost or our loss function by taking the difference between Y and Y hat. Okay, so we take that difference Y and Y hat, and then we calculate the gradients. Okay, so we have the functions for the gradients, or the way we calculate the gradients. We calculate gradients dj dw2, dj dw1. Okay, and this is the gradient descent. We take our current value, our current vector, our current weight matrix. And once we have the gradient, we just take our current value, subtract off the scalar times the gradient, and that's going to give us the value at the next iteration. And then we take, we have two gradients and two weight matrices. So we have W2 minus the scalar times dJ dW2, and we update that. All right, so this is the entirety of gradient descent. Everything else is for the effort of calculating the gradient at that location, right? So we have to figure out what y hat is to help us figure out the gradient. And then we go and we calculate the gradient. But this is the entirety of the gradient descent algorithm, current value minus some scalar times the gradient. All right, and I just repeat this. It says 10,000 times. And this is the result. All right, so these are the resulting coefficients in the W1 matrix and the resulting coefficients in the W2 matrix. These have like no inherent meaning, okay? Like they're values inside the neural network. Values inside the neural network don't really have much interpretability. But we can say, well, what are the y hat values, right? The y hat values, these are what it predicts. It predicted 0.74999998, 0.8200548, 0.929894, right? And so the difference between y hat and y is quite small, right? The actual value is y. We scored a 75, an 82, and a 93. Right here, 75, 82, 93, which we had scaled by dividing by 100. And we got pretty close to those values, right? So there's very little difference between y and y hat. So we have, very little error. If we take a look at kind of how much our costs changed, there's dramatic drop. We hit kind of a flattish region for a little while, and then we seem to have found whatever it needed to happen to kind of improve it, and it became quite flat. Okay, if you take the log of this, we're consistently getting closer and closer to something more and more negative. Something smaller, closer to zero. But that's where we are. Okay. Sorry for going a few minutes over. We will end here, and that's it. So question was, will neural networks or Monday's lecture be tested on the midterm? No. Basically, the content I put on this slide or on this page, and I went over, that's what you can expect for the midterm. So there's not going to be any surprises after that. Okay, have a good weekend. We'll see you guys on Monday.